All right, welcome to our regular Wednesday meeting. It is August the 16th, and to start off, I'm going to recite the disclaimer. And please note that all our meetings are recorded and made available to the public reviewing on our YouTube channel. By participating in the meeting, it is understood that you have accepted the terms. So with that aside, on the agenda tonight, we have Wayne, session 3 of his follow-up on Q measurements. Peter is going to do some RF design basics, so he's going to be talking about a homebrew active probe, and also a follow-up on the Phoenix receiver troubleshooting. And then, of course, at the end, we can have any discussions or a round table, whatever you'd like. So, Wayne, you ready to roll?
Yes, I am.
Okay, take it away.
All right. Screen sharing. Share.
Everybody mute, please.
Screen. There we go. So just before I get rolling on this, my screen is flashing like crazy. I hope you don't see it. What got me interested in the project that I'm currently talking to you about is um, I'm relatively new to radio electronics. I've done electronics for many more years than I have done anything in RF. I was working on a number of filter and RF preamplifier projects, both in LT Spice and in actual builds. And I was having a series of, I had a kind of a longish series of failures in a row. And I took it upon myself to try to figure out what that could be caused by, besides just basically not knowing how to put together a circuit. And one of the hypotheses that I came up with is that perhaps it was related to um, what Q is, the quality factor, and how I was building around my assumptions around that, which were Q was high, and how that affected the actual outcome. So in some part, I've concluded that I was not building by circuits understanding that Q is essentially finite. So to get that, that's going to lead into the actual um, measurement part of this. I've talked about the instruments I was using. Um, in this talk, the case is I'm actually using the one on the right here, the shunt feature. So what that is you're basically putting a series circuit, an LC series circuit, in shunt across the source and the detector, and that causes a high attenuation. And by measuring the depth of the attenuation at the resonant frequency, computation with a spreadsheet will give you what the actual unloaded Q of the resonator is. So unloaded, I mean, is if you looked at this as a circuit with just the resonator and nothing attached to it, you would have a very high, you'd have a perfect Q curve. You'd have a sharp attenuation at this point. But as soon as you put it in circuit, it's going to have, it's going to be loaded by whatever resistances are on either side of it. And that's what brings the attenuation back to more reality. And
Wayne, sorry to interrupt. I know you're sharing. I don't know what you're showing, but we're seeing Q factor measurement part 3, just the title page.
well, that's interesting. I'm having a good time with my second page. So let me just try this again here. What I will do, it says sharing the window, stop sharing. I'm going to stop. Find my way back up to the top of this darn thing. I apologize. I should have actually asked that first because lots of people see the same problem. Where is my first page? Here it is. Okay. I'm going to share my screen again. If I can figure out where I am. Start screen sharing. Select the window.
Select entire screen.
Thank you very much. Been a while, Dave. Sorry. I forgot that. Okay, so now you can see my smiley face, I assume. Okay, do you now see Q factor measurement part 3?
Yes.
Okay, so
There you go.
thanks, guys. Apologies. So here I am on the first page of the actual presentation. What I'm looking at here is 2 test fixtures that I have used. I'm concentrating in this presentation on the one on the right, but the one on the left I'm just using on the next page as an example because it's, I think, easier to intuitively understand what Q looks like. This is, the left one is a standard tank circuit. If you put capacitors before and after it, they have the effect of attenuating the signal. And if you attenuate the signal going into the, if you put that attenuation between the tank circuit and these low 50 ohm input and output, what it does is it sharpens the Q. So if you have sufficient attenuation in this circuit, you're actually directly seeing what the unloaded Q of the circuit would be. And there's a mathematical formula for that. What I was actually using for the most part is a much simpler circuit. The LC circuit here on the right-hand side is an attenuation circuit. So that a more complicated formula, you need a spreadsheet for it to compute what the unloaded Q is. But you think of the unloaded Q as prior to putting it in circuit, this is what the Q might be, hypothetically, I would say. As soon as you put it in circuit, you're loading it down. And the problem I was having, I think, when I was designing as early as I was just assuming there was no load. All right, so on that, here we're looking at kind of an explanation of the rest of this presentation is I'm looking for the measuring the actual Q of an individual component. But when you're putting it, virtually all the measurements I'm aware of use a resonant circuit of some form. So a resonant circuit has both an inductance and a capacitor in some form in the circuit. So you need to understand that they both play a role. So the first thing to do is I'm going to just say if I were to measure the unloaded Q of something, this is a resonant circuit of a capacitor and an inductor in series in the first of the 2 things I was showing you. So there is some insertion loss here. I was unable to attain sufficient insertion loss to actually just read it directly off the screen. So I applied a formula to it. So what I'm actually saying is what you're seeing on the circuit, I wrote 168 by. If you did the math, it's actually showing you 155. And that is because it's insufficiently loaded down in the test fixture I used to do that. And there's very simple math you can use to compute what the unloaded Q would have been. All right, and I'm going to call it 168 here, which is what I measured and computed. When you have a capacitor and an inductor, it doesn't matter if they're a series or in parallel. You can essentially, if they're in series, you can compute an equivalent parallel resistance for the tank circuit, if you would. In series, you just add the components together. This formula is for the tank circuit kind of view of it when they're in parallel. So if you measure the unloaded Q, it's the same formula essentially as the parallel resistor formula, and that's for a good reason, I guess. And you can use that to figure out what say the inductor Q is if you know what the capacitor is, or what the capacitor is if you actually happen to know what the inductor is. And if you were to plot that formula, I'm using a sort of a stretched version of the hyperbolic that this is. I want you to pay attention that I've got 500 at the top here and 4,000 at the bottom here. And that's because the capacitors tend to have a higher potential for unloaded Q than inductors do. If I were to draw this as 4,000 on each scale, it would look like a normal hyperbolic curve would be. Um, I wanted to just sort of point out that if I were to assume that I had a really high capacitance of, say, let's make it 3,000, and I'm looking at 168, if I draw this line across here, what I would be able to conclude is the unloaded Q was very much the same as I'm measuring. And the point I'm making is if one of these quantities is very much bigger than the other, then whatever you're measuring in the resonator is the same as what the actual Q of the other one is. So that allows you to, if you get lucky and you have very high Q capacitors, you can measure inductors. And on the converse, even if you don't have really high value inductors, it allows you to get a reading on what the Q of the capacitors might be. All right, along on that. The first thing I would say is if you're trying to measure things, you probably need to have something that you can count on then. I mean, if I have a formula, you need to know what one of these two things are to a degree. In fact, you don't have to know what it is. You have to know what is bigger than. So if you look at this particular bottom edge, which is very flat, if I'm looking at the capacitance of the Q of the capacitance, so long as it's bigger than about 2,000, I'm probably directly measuring the Q of the inductor in a resonant circuit. Okay. Oops. What I did is I'm following along a body of work done by Wes Hayward. In fact, when I'm doing this presentation, I went back to it because I wasn't really seeing the same values that he seemed to have reported in his document, and I remembered them. So what he did is he took a series of capacitors from the set on the left here. These are mica capacitors that are SMD, and they produce pretty high capacitance near the HF region. So 30 and below, they're all above 1,000. Most of them are above 2,000. So they essentially are sufficiently higher than any inductors that you normally see that you can basically assume that if you're measuring the inductor, if you're measuring the resonator, you're seeing the actual Q of an inductor. This curve on the right, I'm showing it to you because I also looked at the Johnson technology as an exemplar of an MLCC type. Most of the high Q NP0 type capacitors on the market would be in this category. The problem with them from the perspective of the presentation is they don't normally bother to quote the actual quality factor close enough to the HF thing that you can actually understand them. The one on the left is easy to spot because you can see the HF regions on the left-hand side, but they're very consistent with what we're seeing on the mica caps on the left, and they're a lot cheaper, like a 1/4 or under. So should you want to do any measurements on your own, you could feel comfortable, I think, with going online, finding any maker. They all have a line of high Q NP0s, and they will have comfortably high values of Q to measure the Q of, say, of inductors or other capacitors that are lower. So what I did first is I thought I would say to you, I'm interested in the Q of inductors, I am, but the first thing that I had is as a problem with understanding this stuff is I am informed much by the internet. What I can find out there says that the Q of toroid inductors can be assumed to be at least 200, maybe 250. I have since actually found an old Amidon PDF that's available in archive.org that shows that they indeed go much higher than this. But what I did is I went to this and then I looked at the Hayward article, and he said, hey, when I was setting this up, I took a T68 6A. Now, didn't know what that was. 6A is actually a type 6 68 core that's about 50% thicker, if you understand. And he said with the 11 turns at number 18 wire, which I did not have at the time, I got a Q of 399, which is stupendous. That's double what I expected. So I had to try to do that. This is my record of attempting to actually meet what Hayward reported, and I didn't quite make it, but it was interesting. So the first one on this list here, 237, that's probably in the ballpark of what you can expect to see with a good quality capacitor with high Q measured in a resonant circuit. You might see 200 as I normally used to, and that's because I'm going to go back here. And this formula here, I looked at this thing here and I said, oh, Q is probably about 3,500. Back to the formula here. If this is 3,500, this is virtually the same. These two things are equal because this is so small to be significant. But if I were to lower the value of the QC that I assumed to a more moderate level of about 2,000, then it changes the value that I would have computed for my resonance for inductors. So if I come back to here, I was formerly in my first set of measurements reading about 200 for these things. 237 is an artifact of me assuming that the QC was lower, and that's effect of the hyperbolic. And the reason I'm harping on this is that I think that many of the estimates and people are measuring is because potentially people are getting a decent value for inductance Q when they're measuring it. They're seeing like 200, and potentially they're just assuming Q is infinity, when in fact it's finite and kind of low, and it's small enough to modify the actual unloaded Q of the inductor. And that matters when you take it to the next step, which I will shortly. Okay, so well, as I said, I was kind of interested in kind of finding that 399 number. So I didn't get it with T50, but I did have a T60, so I tried to duplicate it. I'm trying to duplicate the same inductance and relative, the same frequency, and I got 262. So just by increasing the core size, it went up. I think that's like 15%. I'm not sure if I'm right. Cool. The next thing I tried was a 106 because that's the biggest thing I had in my kit, and I got, well, you can see I dropped the number of turns because I didn't have, well, basically I wanted to get as close to as possible so I could get that same frequency. The reason for this is I'm using a single high Q capacitor in these things, and I wanted to not move it relative to the Q of the capacitor. So I want it to be the same frequency. So I got 298 at a 106. So learnings here is if you want to build a much bigger PC board, you might improve your Q because you have to have a lot of room for that 106. All right. So the next thing is highlighted in red is I did have some number 20 at hand. By the way, most of the wire sizes I don't actually have numbered on the spools that I have them on. But I had to use a micrometer to measure them and look it up in a table to make sure I was close. So when I say number 20, I'm pretty sure that's right, but might be what, 19? Or might be, I don't think it's 19. It might be 21. Anyways, I got this maximum number of 340, which was cool. So yes, the first thing you get from this is if you increase the amount of material that you have in the toroid core, and I'm only dealing with toroid cores here, yes, you can increase the Q if you need to. All right, so the ladder infill, as Mr. Hayward said, he was using number 18, 11 turns, tightly wound, he said. So I had to try that. So I bought some number 18. So we're looking at a 68.6 core here compared to this one. I had to go down to 19 because 18 is pretty thick. And I found that at relatively the same frequency, it went up to 296. So just comparing to that, to the Amidon PDF, if you should find it, what Amidon said is, look, the best way to increase Q if you need to is use larger cores. The second one is to stuff the core as full as you can with thick wire, because the thicker the wire, the lower the resistive loss in the wire itself, and the more windings on it, the higher the inductance, so therefore the higher the inductance ratio to the core. Um, so that was fun. What this actually tells me, incidentally, is that the reason I'm doing this is I was never sure when I was taking measurements is whether the measure was being perturbed by the inductance being lower than I expected. Sorry, the Q of the inductor being lower than I expected, or the Q of the capacitor. Having done this step, I am fairly confident that if I use a core on use a core that I know the provision of, I can trust it. All right. So let me show you this. Years ago, I went to eBay and I noticed that there were some cheap toroid cores, like types 2 and type 6, available on AliExpress. Now, there was a conversation quite recently about this on our group. So I want you to understand, I'm not saying that there's anything amiss in what was said in the actual um, um, description of these cores. They are, in fact, T52 carbonyl iron powder cores. I'm confident about that. The reason I know this is when I got them 2 years ago, before I thought about what Q might do, is I actually measured them with my LC meter. I have two. I measured them twice. I'll actually use two different cores and I measured them. And after I measured them, I got exactly the correct inductance for the core, and assumed at that point that I had a good core. So then they went into my bin, which is just actually just a bag. So I've got a bag full of these cores. I put the picture here because you can see that the cores are actually slightly different. The ones on the left of the AliExpress purchase, they're slightly bigger and kind of square. And by that means I was able to find all the red cores and almost all of the yellow cores, and measure them when I started doing this Q exercise. So the normal ones, which are essentially amidon or I assume micrometals, they gave this value, 230, all of them. I did 5, by the way. No, sorry, 4 of each. And AliExpress these are the yellow cores, gave 8. Now that could be a whole hurting on you if you were trying to build a resonant circuit and expecting to show something. I did find the one of the missing cores, the yellow one, was in one of my failed experiments. So all I'm saying is, at the time I was doing this, I didn't recognize that it might be important to actually look at the RF behavior of a core. I just used an LC meter, and that was news to me. All right, so you can find bad cores if you really look for it. Okay, so suppose you have good capacitors that you know or trust the Q of, because that's probably how you start this. How would you be able to measure the Q of capacitors that you don't know the value of? So the way you would do that stepwise is you start with those known capacitors, and assuming you know the Q of them, you would set up a series of inductors that have kind of like a band spread, so you could measure across the HF frequency if that's your thing, and then you'd use these known capacitors to figure out what the Q is of these as yet unknown Qs of the inductors. And once you've done that, and if you computed them, then what you can do is use them in circuit with other capacitors that you don't know of. So I did that, but basically this sequence is pretty much what Hayward followed. I did this too. I did it twice, and the second time I was following his recipe. And the difference between what I did the first time and the second time has to do with how he figured out how to map this to values. I was trying to map them to the curve. What he did is he just said, look, if it's in this region from here to about 10, I'm going to call that 3000. if it's here to here, I'm going to call it, say, 2000 and so on. And he had a recipe for that, which I don't actually remember off the top of my head, but I baked that into my spreadsheets and I used it to um, build these inductors. You notice I'm emphasizing on the 106. They give such good Q, I just had to do it. I don't have too many of those. On the lowest frequencies, I settled for a high number of turns on a 61, so that gives me the bottom end of HF and into the medium wave area. And this one will take me up to the end of the HF band. And these are what I was using as my capacitors. I put them into, I showed this last time, but I put them onto pieces of PC board. That's to dissipate the heat a little bit. I'm using these, this is just basic solder braid. And I soldered that onto my test fixtures when I needed to, and I soldered these guys directly on. That allows me to take them in and out of circuit, and I keep them in a box when I'm not using them. At the bottom, there's a couple of Johnson's ones that I just put up here. Should you ever want to have a toolkit to measure Q, I'm going to say you would go with something that's not these things, because the mica, because they're so darned expensive relative to the equally good MLCCs that are out there right now. So basically, I took my 4 inductors, which I showed you on the previous screen, these ones here, and they're, I could put down the actual magnitude, but I put it here. So this is the actual magnitude of the inductances that I had. And you can see that with this kind of thing, I have a kind of a smoothish looking curve. I'll call it smooth because it's hard. It goes right from, that's about 1 megahertz up to 30. So what you can assume that you might be able to do, I guess, is if I stick a capacitor in circuit, I can put it anywhere on this curve to figure out what the capacitor's Q value is, Q factor is, okay? So I went and did that next. I'm going to make this a little bit simpler in this diagram here. This is a clock. Starting from 12 o'clock and going clockwise, I'm going from worst to best. And some things here jumped out at me. First of all, these plastic trimmers have featured a lot in my, when I'm building, say, double tune filters, I generally have a plastic trimmer in there, in the circuit. In some of the circuits I've built, the plastic trimmer is basically all I need. A very small number, it's a very small capacitance mica might be beside it, but generally I'm using these trimmers to find my resonant frequency. And they came in as 135. That's not very high, if you're assuming it's like 2000 and can be ignored. So the first thing is that if you're not seeing what you're expecting, you might wonder if, in fact, the Q of the capacitor is lower than you anticipated. This is a comment directly to my double tune filter experiments that I was using. I only found one dog bone. Mr. Hayward had several. He likes these things. In this particular one, it's at, these are 100 picofarads. It came up around 267. That's about the same as an inductor. If I can remind you of the way the formula looks for combined Q, that would directly have the Q you would expect to get. So if you had a nice 250 inductor, you would get 125 out of it. And should that matter in your circuit, then you would want to know that, I trust. Now I had a bunch of disc type capacitors in my junk box because I collect junk. These came in at the 100 picofarad level at around 350 to 450. I tested a couple. Then I pulled out my silver mica capacitors. Now these are the first ones that I think are temperature insensitive. The sorts of things you would like to use in filters. You don't want to have your resonant frequency wandering all over the place as the temperature changes. And this is only 800-ish. And that's not very high, I would say. I would say it's not high enough for you to ignore it if you're modeling it. You'd want to know that, I would say. I have some, I'll call them random junk box MLCCs bought off of eBay. So there's like a kit of different sizes of capacitors. My 100s gave me, I had two of them. They gave me like 100, 1025, 1015. Excuse me, I'm going to scroll back for a minute to my diagram. Oops, I went too far. Here we are. So 1000 is about here, and it's in the area where if your Q is X, you're going to get the wrong value. Essentially, it's not a lot wrong, but enough that it's enough that you might want to start being concerned about it. However, generally speaking, if you're on the right-hand side of this curve, I'm going to wager it's probably good enough. Okay. I'm sorry, I'm pounding on the desktop as I'm talking. The thing here is actually another Cornell Dubilier product. I found it when I was looking at my mica capacitor, so I bought one leaded one. This one here is, well, higher than this one by a good measure, about double in terms of Q, and would be appropriate if you could afford it. It's I don't actually really didn't compare the prices of these two, but mica capacitors from this particular concern tend to be higher because they're top quality. Eh? Then I fished through my junk box of eBay purchased. You know, you can do this. You can go to eBay. You can buy 1 billion SMD capacitors of 1206, right? So I got my set. Should I ever need them? And I'm still a little bit cautious about using SMD. Anyways, that came up as 2200 basically. So 2200 is very respectable. These are not temperature insensitive capacitors. I believe they would be normally the ones that swing very widely, but that's pretty respectable. And for purposes of experimentation, I would have no problem using those because who cares? Like, I'm only interested in the capacitors not skewing what I'm expecting in my results for test purposes. Then I had my, again, this is a Navy purchase, one of them. I bought a kit of NP0 MLCCs, and that came up to 2255. So that's nice, I would say, for an eBay purchase. Then I fished out of my supply of trimmers. I actually did 3 trimmers at the same time. These two ended up here, and this one ended here. This is an, it's called, I think it's called a ceramic trimmer. So basically, it's got mica. This material here, the material that's white is actually a ceramic material, I guess. And it came in very high indeed. And it's very big too. So it's, if you compare the size of these two things, I guess this trimmer here would sort of be between that line there and the edge here. So maybe not something you'd end up putting in circuit if you don't have a lot of real estate. But that's good to know because I can actually use this crap that I have in the junk box. So that's it for the capacitors. So the main learning I had from this is the capacitors aren't infinite, as I had gleaned from the internet. The capacitors are not sufficiently higher than the inductors that I can necessarily ignore them. So when I am doing my LT Spice models and when I'm doing my calculations, I have taken to, well, considering them, I guess. Last thing I attempted to do, well, second to last, I actually attempted to build a circuit that looks like the, you've probably heard of the Boonton Q meter, which became the HP Q meter, which became the Agilent Q meter before they moved on to better tech. In the heart of those is a variable capacitor, of which I have too many. When I used to go to flea markets, I was not very circumspect in my purchases, and one day I bought a big boatload of variable capacitors. This is a small set of them. I put these into a circuit. I attempted to measure the Q of them across a number of frequencies, and I found they were extremely low, much lower than I, well, hoped, I guess is the best way of putting it. Didn't know what I was expecting. This one here happens to be the one on the left on top of the piece of bamboo, proved to have the best stats. In this circuit, I'm using only capacitors that have 2 or more stators. Now I did this because each stator, I don't know if you can see it, if you can look at the one in front, generally speaking, every stator is connected to ground or connected to the case by a pressure washer, if you would, or a spring. This is brass and the one that's in the front center here. So I reasoned that the more stators you have, the more spring copper or brass is pressing against the stator, which should lower the resistance to the actual outside of the box, which where you attack the say the ground to or the lead to, and that should increase the Q because you've effectively allowed for more conductors touching the stator. As it turned out, that didn't make a damn difference. I have a five stator one that you're not seeing here that appears to have silver coated springs as opposed to brass, and it was worse than the ones you're looking at in terms of the Q that I was able to measure. All right, so on the next page, we're looking at the Q curves for an air variable capacitor. Number 2 is the one that was sitting on the bamboo base. I should introduce the actual magic formula for figuring out what Q is. It's always the same. It's if you're dealing with a series circuit, at least. It's the reactance divided by the series resistance, whatever that is. In an inductor, the series resistance is sort of affected by skin effect, and it's mostly copper, but the skin effect causes the resistance to increase with frequency. In a capacitor, I'm thinking, based on looking at data sheets, I'll talk to that in a moment, that the resistance is approximately constant, but it's the reactance, the capacitor reactance that changes. So having a look across here, what you can see in the formula is if you increase the capacitance, it's in a denominator, so the Q goes down. If you increase the frequency, it's in a denominator, so the Q's go down. Q's should go down. And that's what's shown in the curve. These curves are showing that the highest curves are for the lowest capacitance, and the highest values are in the lowest frequencies. Now, what I would point out is that the frequency is, the variable capacitor at its highest capacitance, which is around 470, brings the Q very low. That's between the range of 100 and 200. So if I were to try to use this in circuit, I would have to use some kind of complicated curve to figure out, depending on where I had my capacitor tuned to, what the actual capacitive Q should be. And because of that, it means for me that I can't accomplish what I think is available in the commercial Q meters, which is essentially, at least if I trust what I'm reading, the Q is not a factor here. You can tune that thing as long as you're dealing with the inductor. You're just basically a measure inductance, or if you are to put a known inductance, you can also measure the effect of another capacitance. So, why am I saying this? That turned me away from a project that I was working on to try to build a proper Q meter using a variable capacitor. If I need to know, I'm going to stay with my set of reference capacitors. All right, so at the end of this, I'm going to say what I learned is you might want to know what the Q resonator is if you're using one by measuring it, not assuming, as I was doing. And again, my assumption was infinite capacitance or capacitance Q that's so high that you do not need to care about it, and just walking with whatever the internet was telling you a proper Q might be for a toroid, measuring it It's a little less than that. It can matter in certain circuits, as I found by simulating it and building it, but for the most part, it may not. You also might want to model your Q if you're inductors, if you're putting them in circuit for the same reason. I don't think, for the most part, measuring the Q of an individual element is necessary. This is just, I mean, even if you're using an LT spice model, you can always add a parasitic resistance into it and a parasitic capacitance explicitly to cover, a parasitic resistance for a parallel and a series circuit. They're different, but you can put them in place rather than necessarily modifying. There's a place you can edit in the inductor and the capacitor for these parasitics, and I find it's more convenient for me to put them as a separate modeled element. If you really need high Q capacitors, you're either going to need to measure them or you're going to need to buy them, because I wouldn't trust what you've got if I was you, because it could be that they're actually not as good as you suppose them to be. All right, so that's it for now. I guess I'll stop. Hopefully I haven't been too long. Are there any questions?
Yeah, I'll start off. I wonder what the Q value would be of these inductors, the cans, the Toco cans.
Okay, so you remember the one I showed a while ago? Did anybody remember this? A while ago, I found an inductor that was cheap. It was and it was on. I would have brought it to you today, except I can't find the darn photo of it. And I was very proud of it because it had a huge resonance. The Q looked tremendous, and I was very pleased with it. And they're available. They come in 6 and 1.4. They don't come with a can on, by the way, but they are the same type of core, I think. Turns out the Q was very low. What I was spectrum analyzer was the Q was actually somewhere around 300, which had I bothered to actually look what was on the screen, I would have recognized, guys. I was busily sweeping in saying that looks pretty good and brought it in the next day. So for your little resonators that are bound to a can, they're not going to be that good. They're going to be small for a Q. And that's based on these things. Now, I didn't hear a response, so maybe you guys have thankfully forgotten about me bringing that in. But I don't think they're high at all. On the other hand, if you're building an air wound coil, those come in pretty good. I tried a couple of these things. I didn't bring them in here because I wanted to focus on the toroids first. Is that okay, Ken?
So when you say air wound, that's on a form, and it doesn't have any adjustable core inside of it?
That is correct. It's on, actually, I'm talking about one I wrapped around a pill bottle.
Okay.
Okay, so simple stuff. Those come out okay. The forms, so the forms that I bought were the same forms that you buy and you wind. And I have both empty forms and wound forms. I did not measure the Q of a form that I wound by myself. So the cores that I looked at were 1.4 microhenries and 6.4 microhenries. This information's out on the internet, but I failed to notice it in time for my big reveal. I did measure the 6.4 one, and the numbers I gave you was 6.4 to 7.5. I forget how high I made it. I doubt I made it all the way to 35 with that because my capacitors wouldn't resonate that high, I'm sure. Be in the mid-20s for about 70-ish. And down at the bottom, which was around 3, was definitely at impressive 35. So they're not high.
Okay. Peter, go ahead.
Thanks, Wayne. Of late, I've actually, Q has never been the subject that I've ever really paid a whole heck of a lot of attention to until just relatively recently. There's been the odd thing that crops up that's got me starting to think on it. But to see if I've got this kind of straight in my mind a little bit here, assuming that you take, say, two capacitors of the same value, one with a high Q and one with a low Q, and they're in a circuit. Are we saying that the one with the low Q, as frequency changes or whatever, the value of that capacitor varies much greater than what's going on in the capacitor with the high Q?
That's an interesting question. Give me a second here while I pull a rabbit out of my hat. I need to.
Or I could read what's
Let me just start the formula first. Okay, here we are. This is what I need to have my eye on here.
Okay.
So you're saying
two identical capacitors.
you're varying the frequencies. They have the same capacitance.
Yes, but the Q values are different.
Yeah, I got nothing. I can't do this in my head. The frequency is going to, if you double the frequency, the Q of both of them will halve. So I think the Q is probably going to go down proportionally, but I'm not sure.
So,
go ahead.
Well, maybe I could reword the question. Instead of putting values to it, then just saying, what is the effect of using a component that has a low value of Q compared to one with a high value of Q? What is the effect on your circuit?
It lowers it. But I can give you a weird example. I don't have a circuit diagram for this, but can you imagine if you have an inductor in parallel with a varactor? To put a varactor in circuit, you really need to isolate the fact that you have DC voltage applied to it. So you generally put a second high magnitude capacitance in series with that varactor. Have you got that picture in your head?
Mm-hmm.
Okay.
Yep.
So I just did that because I was having weird values. I build varactor-based circuits because I want to sweep the frequency. So the Q of 100 nanofarad capacitor is abysmally small. It's like 1 or 2, say. But if you do the math, the actual series resistance of that capacitor in the circuit, in the leg that it's in, is relatively small, really comparable to the actual series resistance of the component that it's in series with, which is a varactor. So it lowers the Q, but not proportional to the capacitance at all. Okay.
Okay.
So I measured. Oh, Jesus! I left it downstairs. I'm sorry.
No worries.
but it was surprising me because I was getting very low results from my Q measurement of a resonant circuit involving a varactor through the voltages, but very poor results. I'm talking about if you assume the inductor being around 250 or 200, I was seeing 60 to 100, 100 being on the high side. So low, but not too low. And I was ascribing that to the varactor. But I got to thinking maybe the cheap-ass blocking capacitors that I have in my stockpile were the root of the low capacitance. So I did some math thinking into it. And it turned out that you don't need any Q in that. In fact, if you're looking at 1 or 2 in terms of the capacitance, the math I'm using doesn't actually work very well. The formulas that you're using, for the most part, assume Q is greater than 10. And so when you're doing the math, if it's lower than 10, it gets a little bit more complicated, but I'm going to say it's going to wash out. The fact is, go ahead.
I was going to say, so really, another way to look at it would be if you're using components that have a low value of Q. Let me start. If your circuit is not performing the way that you think it is performing, it could be the result of the fact that some of the components you're using has a low Q factor.
Yes, that's very accurate.
Okay.
And I did observe that. Some of the problems that I have seen in the past, I can attribute to that. Not all of them. Some of them were just bad designs. Okay. So I can say that if you're not cognizant of where your Q is at, as it were, in the way you build a circuit, you can make a difference.
So just one last little statement on my part here before I guess turn over to Dave there, then really would be, if you've built the circuit and you've measured your inductors, you've measured your capacitors, and they're all within spec of what the design calls for, but doesn't but the circuit doesn't perform well, it could be because of the Q factor.
Measured, you mean measure the value of the magnitude of it?
Yes.
Yes, it could be.
Okay. All right. That's good. Okay. Yeah.
Not necessarily, though.
Okay. Well, yeah, of course. Otherwise, we would find another hobby. Thank you, Wayne. Appreciate it.
No worries.
Go ahead, Dave.
Yeah, Wayne, from a very simplistic view, I'm going to follow up on a comment Peter just made about you've got a circuit and you accidentally put in a component that has a substant or a lower Q into that circuit. Now, wouldn't, from a very simplistic perspective, wouldn't that change the overall Q and cause it to lower, and thereby increasing insertion loss and impacting your bandwidth?
Yes, that's exactly right. I actually have some slides that follow this that I didn't want to show, but basically the reason I was doing this is because I'm doing filters, right? So there's two ways. Oh, let me just say it this way. I always use multiple resonators, okay? One way that you can increase insertion loss is to manipulate the coupling between the resonators. That doesn't affect the Q of the resonators. That just affects the coupling. And if you make the coupling too tight, you will get a lower Q. Sorry, say that again. You'll get insertion loss. You'll get a higher Q. Apologies. But what happens is if you squeeze that to its utmost limit, sooner or later you're going to impinge upon the available Q that's in the underlying resonators. So maybe I should just see if I can explain this. I'm not going to do the demo. Do I have it here? This is what no, that's not it. Where's my demo? Do I have a demo?
And that's why, Wayne, that's why you see that when you're tweaking, you build a crystal filter, you tweak the coupling capacitors between the crystals, because that'll help you to realign like the Q, because each crystal's got its own little Q,
Mm-hmm.
so its own little Gaussian peak. So by changing those capacitors, you're shifting those peaks around and also broadening them to get a nice overall smooth Gaussian shape without a ripple in the passband.
Correct. So this is where I sit mostly. I'm dealing with multiple resonators. So I'm dealing with double, triple, quadruple tuned filters. So these guys, if you are exerting too much force upon them by trying to crank the Q up by lowering the coupling capacitance too far, they additionally add more. They lower the increase the insertion loss further. What I'm looking at right now is what's the relative weight you should assign to the importance of the Q of the resonator versus that central coupling capacitor. And basically what I'm finding is the coupling capacitor does more than the actual Q of the resonator does in terms of affecting the insertion loss that you essentially see to a certain point. And after that, you're just not going to get, you're just going to get higher and higher insertion loss. So if you were to imagine these resistors showing on the diagram here, I trust you can see it. These represent the Q that I've assigned here. If I were to take them out, they would be the kind of circuit I used to draw, because I didn't think there was, the resistance here mattered. Also, I would use transformers instead of this capacitance. So the reason that you don't normally have a problem with Q in the types of circuits I'm dealing with is if you're using a transformer at the beginning and end, you generally can't set the secondary of the transformer to a high enough turn ratio, come close enough to the Q of the actual resonator to make a big difference. And it's all driven by the coupling capacitor itself. because normally you do transformer as opposed to, like, you have the inductor here and you have a small number of turns on it to connect to your source, and that gives you your 50 to whatever transformation. And that's what I've been working on in terms of trying to understand is it me trying to turn up the secondary too high? Like if the transformer has a high secondary to primary ratio, is that driving the performance down or not? Is what I was looking at.
Yeah, and
When I build these things for test, go ahead.
no, I was going to say there's a huge rabbit hole you could go down here, because the transformer itself is going to have some kind of reactive impedance, as well as it's going to have some kind of resistive loss, and that's going to potentially impact your Q as well. So this can get really, really messy really fast.
Yeah, I live in that rat hole. Thanks, Dave. Yeah, so the most common design, and the one that works very well, is to use an inductor, both as a transformer and as the resonant element. And the inductance that you're using is way too small for it to be considered to be, as it were, independent. It's one way you could do this is if you look at the circuit here and just interpose a second transformer where the C3 is, make it out of a high permeability ferrite and a very high turns ratio. And then you could say, well, that transformer is so high in inductance that it swamps this little inductor here, which is actually the resonance that you actually see. And I do that all the time, and it makes sense to me because when I'm building circuits, it's easier for me to separate the left hand of the circuit as a separate piece. I just build a little component with a type 61 or type 43 core on it, and I wrap a huge number of turns on it and a small number to the primary, and I use that as my source. And that allows me to look at and isolate the effects of the Q in these central ones here. Sorry, talking too much.
That's fine. One other question, Wayne. If you go back to that formula you had where you show how the Qs combine.
Yes, near the beginning, as I recall.
Yeah, it was like the first slide right there. That slide. Yep, that's it. So if I was to understand this correctly, okay, forget about the fact that you're using the slide showing you how do you measure the Q of a unknown capacitor, but just that formula in itself. So what that formula is telling me, that your overall Q of a circuit is a parallel combination of the existing Q plus any Q of a component you're putting in. It's a parallel combination of the both. Is that accurate? Is that correct?
That's very accurate. It says that the actual Q is smaller than any of the individual things that it's connected, that's driving it. And it allows you to work with, it's the parallel resistance rule, basically.
Right.
Actually, it comes from this because the underlying math involves, Q has a parallel resistance, basically, when you do this stuff. And that's
Right.
where it's coming from.
So then wouldn't, coming back to Peter's question, which Peter, by the way, that was a very interesting question. You know, if you're going to substitute, you're going to replace a part in your circuit, you'd want to replace it. And maybe this is what you and Peter decided during his conversation, is that you'd want to pick a part with the highest Q. You'd pick a capacitor. You're going to replace a capacitor in a circuit, in a resonant circuit. You'd want to replace it with the highest, like a coupling, for example, coupling capacitors, right? You'd want to replace it with the highest capacitors with the highest Q, because that's going to have the least impact on the overall Q of the circuit. Is that?
Okay, so that actually wasn't correct. A coupling capacitor, like a 100 nanofarad thing that you stick to keep the DC out, is generally not inside the resonant circuit. You know how you look at the, it's before the resonant circuit.
Yeah,
So
but
I've
there's
done
a
some
couple in.
LT spice modeling to validate this, by the way, just so you understand. It doesn't make a material difference for a couple of reasons. If I were to look at the math, I didn't use this as a coupling capacitor. I used this with a coupling capacitor to isolate DC voltage for a varactor. And what I'm actually saying is it doesn't make in that arrangement, it made very little difference. Actually, it does make a difference. It's about equal to, if you have a low value Q for a capacitor, you would indeed notice it. But that's actually inside the resonant circuit of a LC circuit, a tank circuit. You can think of the leg, there's an L leg and there's a C leg. The C leg has two capacitors in it. And I put 100 nanofarad capacitor there with abysmally low Q. It makes a small difference, is what I'm saying.
Okay, so
And
then
it's because the magnitude of the capacitor has to be taken into account in the in the computation of the. Let me try this again. The magnitude of the capacitor affects how you do the computation, and it's down. Give me a second.
so it's only applicable. That formula is only applicable to components that's going to participate, or it's going to, I don't know the word. It's going to couple. It's going to be part of the overall Q of that circuit. So it only applies to components that are part of that resonant circuit.
That is correct, as far as I know, and I have tried
Okay.
testing this in numerous
Okay.
ways. Yes.
Okay, I
So
thought.
if you, the reason that works out that way is a low Q component, such as a blocking capacitor, has a very high magnitude of the capacitance, and they somehow dissipate the effect, if you would. I do not think that blocking capacitors in any circuit that I'm thinking about, at least, are going to affect anything to do with it, unless they're right inside the actual resonant circuit itself as part of it. So you will see an effect in anything involving a varactor and a blocking capacitor, because varactor Q is small and the blocking capacitor has just enough to notice, if you would, but it's not a lot. And that was a surprise. I just figured that out the last couple of days, basically, because I was looking for a reason.
Okay, that's good. This is good. This is excellent, Wayne. This is good food for thought, because it's kind of taking us into areas that we never thought of.
And for the most part, that's probably because you don't really need to worry about it. When I did my analysis, what it's taught me is there is a reason why I need to be concerned, but the reason I wasn't seeing, I had, shall we say, a serial failure rate is not all due to Q at all. It's just bad design, basically. Most of it is something I need to go back and understand what I was doing better. And I can kind of knock that off my bucket list, if you would.
Okay. Anybody else? No, very good, Wayne.
Very good, thank you.
That was very interesting. Like Peter said, this is something I've got to look into and try and understand what's going on. Thank you for bringing up this presentation.
Great. Oh, I didn't show the last page, but what you want to do is check Wes Hayward's. It's called The Two Faces of Q. You want to look at his materials, because he's like an authority here, and I was mostly following along with him. So have a look at that, and it will help you. And what else have I got? I closed my file, but anything by Hayward on Q, if you just Google it, you'll find he's done some research in this. He apparently was looking into making DXing with AM radio broadcast stuff, so he needed high Q stuff to do that.
Very good, very good. Anybody else have any comments or questions? Okay, thank you, Wayne. Peter, you want to go ahead?
Sure. Which one to start with? I guess I'll start with the longer one first. Not that it's that long in the scheme of things. I'm assuming we can see that?
Yep.
Okay, homebrew active probe. This is a subject that's been cropping up off and on over the years, and maybe even more so really in the last year or so. And well, here we go. So the first one we took a look at was the Poorman's active probe, and this circuit actually came to light, I'm going to say, before COVID. And it was a circuit that was in the Elector magazine. I forget what year it is, but you can Google it and it crops up easily. And then some guys in the Ukraine lifted the circuit and started to produce these probes and sell them on eBay. I think when they first showed up on eBay, they were probably, I think, just over $10 or something like that. And I think now they're a little bit over 20. Anyway, I was lucky enough that Dave E3EAC in town here lent me his. He might be sorry that he did lend it to me. I'll come back to that in a minute. And I started to make some measurements. I've circled a couple of spots here of interest on this circuit. The one in the upper right there, why they would put a reverse dial in like that for reverse polarity protection, I'm not sure. I don't think I would do that. Maybe put it in series. But I don't think that's a good method to do it that way. And the capacitor on the left there, C1, is an interesting one there where they have the probe pogo pin that comes in on one side of the board soldered to a pad, and then on the other side of the board is the other side of the capacitor and leads off into the circuit. And I think that's in the range of 0.5 picofarads, I believe. Although I'm wondering what the difference is. Do you go that way, or do you put a couple of 1 picofarad capacitors in series? Does it make any difference? I don't know. Maybe somebody might comment on that. So here's a couple of just quick stats of the probe in comparison to the Agilent, and they both have an input impedance of 0.75 picofarads. The Agilent at 1 mega ohms, and the other homebrew probe at 10 meg. The bandwidth, it goes up to, for the homebrew one, down to 100 kilohertz, up to 1.5 gigahertz. I don't really need to go that high or anywhere near there. But and then in the table 2, they're just showing a selection of 4 MOSFETs. 2 of them are pretty much identical, the 998 and the 991, coming in at the picofarads, 2.1 on the gate, and a noise figure of 1 dB. I have a few 998s. I'm not sure how many I've got, so that would be the one of choice. So getting back to why Dave might not be happy with me, I started to make some, there in the circle on the left, you can see his probe. Dave mounted it into a nice little pen case there, and away we went. So I managed to do, I don't know, half a dozen measurements or so, and then unfortunately the tip on the pogo pin popped out, and all that was left was the sleeve that it went into, which is where the spring-loaded mechanism is as well. But since I had just started the measurements and I needed to redo them anyway to validate, I decided to, well, let's see if I can jury rig something. So I put a piece of wire and pushed it in against the spring. And then I had my son, while I'm holding it all there, put a couple of pieces of tie wrap around it, around the ground wire to see if it would hold. And it did. And then I soldered an SMA connector onto a piece of scrap PCB so I could just leave everything alone and not touch it and see if it would work. And it did. So I ran from a +5 dBm down to -95 dBm and got a pretty good linear response down to about -75 before it started to kneel over. I'm not too sure why. I did this with a signal generator connected to the probe and then was reading in on the spectrum analyzer. And I'm not sure why I just didn't put the tracking generator into the probe and just went that way and then scan. Then I could scan not only amplitudes from the tracking generator varying there, but I could have also been scanning across the frequencies. But I didn't think of it at the time, and maybe the broken tip threw me off, and I just did the measurements this way and then was happy. While I was doing this, trying to understand the circuit a little bit and how that MOSFET was working and how low could I go, because I would like to get down to about minus 110. And so I started looking at the data sheets, and I'm not really understanding completely what it's telling me. Up here, it's telling me the minimum voltage between the gate and source 6. And if you kind of look at the 5-volt regulator with the voltage dividers here, the biasing and all this kind of stuff, I don't think that gate to voltage is anywhere near 6. I think it's more like down 4. I tried to do a little bit of some quick simulations with LT Spice to see what I was coming up with, and what I've done so far kind of shows it down. I think at one stage maybe 4 or even way less than that. So I'm not too sure how that all works. I guess I have to understand maybe the data sheets and work with MOSFETs a little bit just to get a better understanding of what's going on there. Unless somebody has a comment later about that, I'm not quite sure how that works. I must be missing something. So if the data sheet says I need a minimum of 6 in order for it to work, and I'm not getting anywhere near there, anyway, we'll see what happens as we go forward. And then when I got curious, I used the Chat GPT here, and I just asked it, okay, what can you tell me about the minimum gate source voltage, just to see what it had to say. And it kind of came back with, what I figured it would say, but I thought it was kind of a well-written response. Here's some examples of probes. The ones at the top is not much more different than the poor man's. They got a couple of extra diodes in there. A lot of the stuff you'll see on the internet for homebrew active probes, a lot of them are a lot like the poor man's probe circuit with just some minor changes to it. The one on the bottom actually has an AD8307 on the output of the probe, and I think this particular probe here, the guy was just designing it as a, just to be able to detect some kind of a signal source. So that's why he put the 8307 on there and just monitors the, I guess, the output voltage. So that's one way of doing it. Here's another circuit. This one here is one that this gentleman wrote a thesis on homebrew active probes, and you can see it's pretty much identical to the poor man's probe. Just a little bit of a changes here on the output. He added in a 33 ohm resistor and another capacitor and some filtering off the side here, but otherwise they're pretty much the same. Biasing's a little bit different, but basically it's the same circuit, and the voltage is a little bit different too, higher in this case. So I went to the Mr. Carlson's lab and viewed this video of his, probably 3 or 4 times now. And he designed this probe for a very specific use, that the project that he was doing that was either 40 or 45 megahertz. So he aimed this circuit at that, or designed it with that in mind. But what was nice about his video is that he goes over in detail of what every component is in there for and why. The only problem with this particular circuit now is that try and find a 3SK74 MOSFET, or try to find a BC817 transistor, so the components need to be upgraded or modernized in this case. The ALT1812 op amp he's got in there, that's available, but I think it's a bit pricey, that one. I'm not sure now. I think it's about $12 or something like that, but it's something that might be considered as well. This is just I was on this kick about understanding MOSFETs and minimum voltages and all that stuff, and this is basically the same. Although in this particular chip that Carlson is using, the capacitance is much higher than what the BF998 is. Here's another circuit that somebody's had come up with for his probe. he put in a filter in here. He calls it an anti-spike low-pass filter. So I think there's a spike that he discovered that it was in around the range of 800 megahertz or something like that. So this was supposed to take care of that. But again, it's basically the same circuit as the Poorman's. Just another additional capacitor at the front here. He's got going to ground. Different value of resistor in here, but pretty much the same thing. Same biasing up in this area up here is the same as the Poorman's. So Dave EAC sent me an article from the 73 Amateur Radio Today magazine back, I think it's August of, well, I got it in the credits anyways. And this is what I was starting to think about, is adding a amp after the MOSFET. And in the case of the diagram on the lower right, he's using a MAR1 or a MAR2. And I happen to have a whole slew of MAR 1, 2, 3s, 4s, I don't know, I can't even remember now, and a bunch of 6s that Dave and I bought from Mini Circuits a few years ago at Dayton. So, so I think that's probably going to be one of the first circuits I'll try here, is something similar to the one that's at the bottom right there. I don't think I have an NPF 102, so, but like I said earlier, I got a bunch of the 998, so that would be the one of choice. So this might be, it'll likely be a circuit that I'll give a go to. So points to ponder here really is, okay, redesign the Poorman's active probe. Yes, I think so, because minus 75, 70, 75, I want to go lower than that. So that's where I'm saying, okay, do we add an LNA after the MOSFET? I think that's the way to go. Or update the components, the circuit that Mr. Carlson is going on is another option. And of course, the other one is the goal of measuring a minus 110 to 115 dBm signal. Am I being realistic? I don't know, but of course, we really don't know until we try. And then this is just some of the sources of where I got some of the information from. And oh yeah, the magazine Amateur Radio Today, August 1998. And that's it for this particular presentation, Ken.
Good. Excellent. Any questions, anybody? Go ahead, Dave.
Yeah, I have to hassle him. He's not going to get a free ride. Hey, Peter, go back to that chart you drew. There's a table you plotted. It's one of the early slides. Yeah, that one.
This one?
So what's X and Y here? What are the axes?
I knew it. Okay, the one on the horizontal, the 5 down to minus 95, that is the value of the signal I was putting into the probe. The value on the left is what I was reading on the spectrum analyzer. I'll be honest with you, I didn't expect it to be reading like that. I thought it would be different, but that's what I was getting. And I figured I'll try and figure out later why it's reading that. I didn't expect it to be reading that low, but I was just happy that I was getting a linear response, and I think I would worry about the numbers later. But what is accurate is the ones at the top.
Yeah, just the slope of that line is what your attenuation is. You see, you've got your attenuation. You put in a 5 dBm signal in, and you get a minus 40 dBm signal out. So you've got like what, 45 dB of attenuation. So that line, the slope of that line, of that straight line, is going to be your attenuation as a function of frequency, right? That's all that means. Now I notice you're putting in 5 dBm there. Could you go back to the data sheet? Okay, so that 5 dBm, no, there was another slide. That 5 dBm you're putting in is awfully hot. There's another slide you've got that shows the input range for the voltages. Yeah, here, right here, that slide. So if you look at the Agilent, for example, let's just say, were you using the Agilent probe, or is that a homebrew probe you're measuring?
No, It was the poor man's probe,
Okay.
homebrew probe.
So, for example, notice the 1 dB compression point, wasn't measured. It's saying it's 0.3 volts RMS, 5
Yes.
dBm feeding in. Okay, it's going to be way above that 0.3 volts RMS for the adjuvant. And I suspect it's going to be too high for the homebrew probe. So you have to be careful how hot of a signal you're feeding into this thing, because you could cause some damage to
Yeah,
it.
don't say that because David EAC is on this call.
Yeah. So like I wouldn't be feeding it a 5 dBm signal into that probe. I think you may cause some damage to it. But anyway, so that's just a caution. If you go to the schematic showing the yeah, that's fine. Okay. So Peter, if you look at this, okay, the gate, see the gate where the 10 meg ohm is connected to? That's the first
Yep.
gate. The gate at the top is tied to the whatever that is +5, so that gate's always turned on. Okay.
Yes.
So the second gate is the one that's varying the voltage. So that gate in this configuration, the output there above R4, this is a common drain amplifier. So the gate voltage is going to be the same voltage at R4 minus the only difference, it's going to be different by the what's called the VGS, the gate turn on voltage. So or the minimum VGS, they're going to differ by that voltage. But the reason it's also called, I think, a source follower, because it follows whatever input you put in is what's coming out here. And the reason you use this is because the impedance of the gate of the input impedance is extremely high. Now, if you go over to the field effect transistor model, I just want to caution you with one thing there. It was the last diagram. You said, oh, you're going to try this with the MAR6.
Yeah. Yeah.
Okay, so if you pull up that diagram, it was right down at the end. Yeah, right there.
Right here.
Okay, see those NPF 102s? Okay, those are FETs. Those are field effect transistors. They're not MOSFETs. They're not, when you bias them, they need a negative voltage at the gate. Notice there's a 1 meg or 100K to 1 meg ohm tying it to ground. Okay,
Yeah.
because the ground has to be at ground or negative for this transistor to turn on. So you have to be careful with how these field effect transistors work. Just be
Well, I would think
of that,
MOSFET.
because a MOSFET needs a bias to go and turn it on. These field effect transistors, they need a negative bias to go turn them on with respect to source.
Well, I figured I wouldn't say following this schematic like this and just plop in those other components. We'd have to rework the whole thing. But I was thinking, take the poor man, basically say, take this portion, a MAR, and use a MAR after the BF998.
Yeah, that's fine. No, I just caution you about those MF 102s. They're not MOSFETs. They're a FET, a field
I
transistor.
don't even have any anyway.
Yeah,
So,
and they work differently than a MOSFET. So the bias is
right.
different. That's all. That's all I wanted to draw to
Yeah,
your.
and the other thing, Dave, is I did take a look at the +5, and I looked at what that equated into voltage and whatnot and all that kind of good stuff, and I thought it was still well within range of what the MOSFET said it could take. So I wasn't too worried about blowing it, but I certainly wouldn't have gone any higher.
Anyway, that's it. That's all the comments I had to make. I just want to point out a couple of things to you about that. Hopefully, that's going to help your understanding.
Yes, it did actually. Thank you.
Very good. Oh, wait a minute. Michael had his hand up.
Yeah. Peter, the graph, the one with the nothing on the X and Y axis. Can you go back to that?
This one?
Yeah. So the horizontal is, you said, what did you say that was? That's
Signal in dBm.
and the vertical is what? Signal out?
Yeah, that's what the spectrum analyzer was reading.
In a night, I don't know enough about this, but it seems to me ideally, what you get in, you get out is what you ideally.
Well, the poor man's probe is not 1-to-1. They say like a 20. I think they rated like a 20 dB minus 20 dB, which
Yeah, you can see it's not 1-to-1. Yeah, okay.
This still doesn't show it, but at the time I really wasn't too worried. I mean, it was something that was bugging me, but not enough to say, okay, well, I got out of it what I wanted, and I wanted to see a linear response, or how low could I go before it kneeled over.
Okay, I just curious. Okay, yeah, thanks.
Yeah, as long as that line's linear, okay, and it's got a slope, and it looks like a pretty clean slope there, right up to about almost minus 75 dBm. So it looks linear to that point. That's a good thing. And I think that that loss you're getting, you could think of that as insertion loss.
Yeah, oh, for sure. The thing is, I just didn't expect the insertion loss to be that great, but I didn't spend any time really to try and sort out what was going on. But the thing too, I didn't go any lower than minus 95. I kind of wish I had now. But the thing is, the SA was still seeing that signal no problem, even though it's healing over. So you could say, if I go back to my original goal was to be able to detect a signal, these really low signal levels. Sometimes it's just good enough to know that there's a signal there. But of course, once you get with this particular probe the way it is, once you get to minus 75, then you won't be able to discern a relative value to each other. Certainly from +5 down to minus 75, you can. It's a nice linear slope. But after that, it's probably, at least the way it's configured now, it's only can say after minus 75, then all you can say is, well, there's a signal there. What its amplitude is, who knows? And even relatively, you can't tell a difference between minus 80 and minus 95.
Well, you talked about adding an amp. If you add an amp at 45
Yes,
dB amp at 50 ohms, must be at 50 ohms. If you've got 45 dB of gain, then your goes in is going to match your goes out.
yeah.
And Peter, you said the horizontal axis is what you put into using a signal generator, right?
Correct.
Yeah, and your SA told you, the SA looking at the output with the SA is the vertical. Okay, thanks.
Yeah.
All good stuff. Good. So we're gonna build a bunch of these
At some point. Well, you know what? If you're happy at minus 75 or what you can see the performance, what you're seeing right there, then the way the poor man's is designed as it is right now is sufficient. I'd rather build one than go to eBay, but it's up to you, individuals. But I would I'd like to see if I can get it down to, like I was saying earlier, minus 115, which is I think around the S3 level. I'd like to get down around there. Who knows? Maybe I can go lower. Who knows?
Yeah, okay.
Anybody else? Okay. Part 2, Peter.
Okay. Let me just. Whoops. Okay, we've already covered off a lot of this. I just wanted to do an update to what I was finding with the Phoenix. And actually, while Wayne was talking about his presentation, it got me to thinking, maybe that's an issue. I got a Q problem. with a capacitor or something like that. But then that was all taken away when we talked about the coupling not being a big factor. So anyway, I guess we can see that.
We could before. It's gone now.
Oh, is it?
Yeah, there it is.
Okay. If you remember, this is what I was showing last time. This was just basically the blue was the proof of concept board versus the Phoenix board. And that helped me identify what's going on. So I've done an update to that since then. Oh, there's Dave's probe there. So I've done an update to it. This time I've included a third line that I called Phoenix A, and this is after I made some changes. And basically, those changes were increasing the level input to the VFO and BFO. Now, the reason why it was too low in the first place was because doing the proof of concept board, we controlled the input to the mixers via the signal generator settings. When I transferred over to the Phoenix board, I forgot that we put in attenuator pads on those ports because the Park SigGen that we were using for the controller is hot. And I just didn't think about that for quite some time. And anyway, so I ran the tests and away we go. So over here on the left, the repaired Phoenix is in the red line and the bad Phoenix is in the orange and proof of concept is blue. So as expected, we're following along. And then here's where the proof of concept board stays here, but both the bad Phoenix, for lack of a better word, and the repaired one follows the same trend, which at this stage of the game is expected. And this is where I thought, oh, maybe this happens to be the junction right where R6 and C7 is between the output of the LT1253 and the input to the bandpass filter is. And I thought, oh, well, maybe that's the Q of this capacitor is bad, and that's why this loss is greater. But then we had that conversation that says Wayne was mentioning that in effect that would not have much of a dramatic effect. Anyway, so we'll let that go for now. The Phoenix that I fixed up, it's still showing the same thing at the bandpass filter. And I measured it again to confirm, obviously. But why I'm getting a higher output on the bandpass filter versus the input, I have no idea. Still don't. The proof of concept board, I rechecked again, and yeah, it shows what you would expect. You lose a couple of dB going through the bandpass filter, but the Phoenix board is showing like the bandpass filter is acting like an amplifier. I have no idea what's going on there. Okay, so I'm just representing here. This is the BFO input, and you can see where mouse keeps disappearing. Here's the where I had the signal levels were very low, and you can see where I was having troubles and obvious reasons why, very low signal levels there. So here is where I jacked up the signal levels, and sure enough, it's now responded. Now, I have to say this came out lower than I thought it would be. Yes, I am a little bit lower here than the proof of concept board, so maybe moving this up to here will bring this up again even a bit more. Although over here, it finishes off pretty close to what's going on here. I should have made notes here. I'm wondering why why did I circle it? Oh, probably because here I'm showing a gain from the input to the output, which is expected on that mixer, but here I'm still continuing a loss. So I need to go back into here and have another look. But regardless, the Phoenix is now working very, very well. It shows here probably not quite as well as what the proof of concept board is, but it certainly is performing quite well, and I've been listening to it and works quite well. I did a quick recording here. One's a sideband signal and one is a CW signal. I believe, again, I should have made notes here, but I think the sideband signal is around an S5 or 6. There might be another station in there a little bit low.
Yeah, 2 talks and this damn thing coming up in 2 weeks. I'm gonna be in a room full of people twice. 2 hours in a room full of people. That's really smart, huh? Oh, well, yeah. Where are that? Makes them laugh at you. Yeah, you can't really talk good with a mask, though. Yeah, I know. I know. Half the things like that.
Yeah, I think the louder guy was in around the S5, 6 kind of thing, and then the other guy was a little bit weaker, was down around the S4 mark. And the CW signal, I forget what level this one was at. It was not much higher, maybe S7, S6, S7, somewhere around there. And then a little bit of fading. Eric should be able to copy this. Okay, so there's the my latest update to getting my Phoenix up and running. Thanks, Ken.
Very good, Peter. Anybody have any questions or comments? Oh, good.
Actually, you know what, Dave, it would really be good if you could measure a signal level on your bandpass filter input and bandpass filter output. When you have time.
Yeah, sorry, Peter. I'm not going to be able to do that for quite some time. I just got too much on my desk.
Oh, okay. Oh, no worries. No worries. I mean, like I say, the proof of concept board works great, but why I'm getting an increase on the bandpass filter here, I have no idea.
Peter, I would suggest you look at impedance mismatch, because if you're now, is this power you're measuring or voltage?
This is power.
So you're measuring this with your spectrum analyzer.
Yes.
Okay, so you're measuring it on the output of the bandpass filter?
Yeah, right here is the input
with
bandpass filter.
With nothing connected to it?
No, everything's connecting. It's all running. I've got a signal. There's a signal being put in.
You've got an impedance mismatch. Peter, you can't connect, a 50 ohm load in a terminated circuit.
Yeah, but don't forget, Dave, these circuits are identical. The proof of concept board and the Phoenix board, they're identical.
Yeah. So Peter, I don't know. All I'm saying is that anytime you see that, a voltage, a power level changing, or I would almost say this looks like a voltage level, because if a voltage level goes up, that's because there's an impedance mismatch. You're not transferring the maximum amount of power. But hey, I don't know how you're measuring this, and I don't really, I can't get into this right now, but it looks like there's some kind of impedance mismatch there.
Well, if there's a mismatch, then it's either got to be from the TR1 over here. We're this area here, TR1. That's the matching transformer. Like, let me just right here. There's an increase in the signal level here compared to here.
Say that again, Peter.
I have a signal level here at an X level, and I have an increase in the signal level here.
That's because the SA612 has gain.
Yeah, but the 612 isn't until you're over here, and this will be going to pin 1 on the 612. The input to 612.
Hey Ken, he's talking about a passive component. He's seeing a gain across a passive component.
This is the QRP filter.
He's seeing a gain across a filter where he should be seeing an insertion loss.
Oh, okay.
Yeah, the proof of concept board shows a loss, And it's the same filter I'm using. I just took it out and plugged it into the Phoenix board, and now I've got an increase. The only thing that's different between the proof of concept board and the Phoenix board is this transformer.
Well, then I'd say check into that first.
I guess. Anyway, that's what we got.
Okay. Question, comments? Very good, Peter. So, I don't know if anybody wanted to bring up any discussions or anything, or maybe we can just do a round table or see what everybody's working on their bench.
Hey, Ken,
I'll save the round table.
Ken, I have to
Yes,
run
sir.
and I have to stop recording at this point because I have to go. So the rest of the meeting is not going to be recorded, unfortunately, unless
Okay.
someone hits the record button.
Okay. Well, I'm not set up to do a recording, so I guess I should
We
learn.
got the main stuff anyways for the meeting.